Section 7.4, integration of rational functions using partial fraction decomposition. Well, like the title says, the method relies on decomposing partial fractions. This is one topic that you have covered in your pre-calculus course, not the integration, of course, just the decomposition. That's depending on where you took pre-calculus, you might have covered it, you may not have covered it. So, okay, what is partial fraction decomposition anyway? So, let's go back to a very basic intermediate algebra problem, so we can see the difference between the problem you did back then and the problem that we are going to do today. Well, basically the entire week. We're going to spend a whole week doing this. All right. So they're asking us to simplify this expression right here. What would you do to simplify that expression? Any ideas? Common denominator, right? So here we have two fractions, but unfortunately these two fractions do not have the same denominator. For example, like 1/2 plus 3/2. Well, we can just add the numerators. That's 1 plus 3, which equals to 4, and keep the denominator, right? However, it's not the case when we have like 1/3 plus 1/2. Well, we cannot add 1 plus 1 and 3 plus 2. No, we don't do that. We need a common denominator. That's 2 and 2 and 3 and 3. And that's 1 times 2, which is 2. 1 times 3, which is 3. Over the common denominator, that's 5/6. So that's how we did it with numbers back in elementary arithmetic, I guess. And so the same idea will be taken here when it comes to combining fractions together. Well, let me rewrite the whole expression because I need space. So in this case, we don't have the same denominator. If both denominators were x minus 3 or both denominators were x minus 2, we would have just combined them together, having that denominator in and the common denominator, and just do the indicated operations that we have with the quantities in the numerator. But it's not the case. So in this case, the LCD is the product of these two. That is, we need to multiply by x minus 2, and we need to multiply by x plus x minus 3. So now we have the same denominator, x minus 3, x minus 2. And in the numerator, we're going to get 3 times x minus 2 minus 2 times x minus 3. So we are essentially done with the combination of the fractions. Now we need to simplify the quantity in the numerator, that is. So we're going to distribute. We're going to distribute these two quantities. And combine like terms. So that's going to give us a 3x minus 6, and then minus 2x. Negative times a negative, be careful, that's a plus 6, and divided by x minus 3, x minus 2. So of course we can cancel out these terms here. Well, negative 6 plus 6 cancel each other. And what about the x's? We have a 3x minus 2x, which is x, over x minus 3, x minus 2. And that's final answer for combining the two fractions together into one single fraction. So that's what you learned how to do back in intermediate algebra. Well, again, in some cases you were given fractions with the same denominator, you just did the indicated operations. In some cases we needed to do some work in this case to find the least common denominator. Now, so for this section, what we're going to do is the backwards process of combining these fractions together, and that's what we call partial fraction decomposition. Alright, well, so this is what we're going to do. Decompose x over x squared minus 5x plus 6. Well, number one, every time we have a partial decomposition problem, our first thing to do is to factor out the denominator. And that's what it's going to give rise to the many different partial fractions. So let's have a look. So let's factor out x squared minus 5x plus 6. Well, in this case, we can use the double bubble method. Because the leading coefficient is 1, we can just go ahead about that. And we're going to look for factors of 6 that add up to -5. What are those factors? -3, -2. And we'll keep the x at the top. Alright? So that's our first step in here. Well, so to decompose this into partial fractions, notice we have in this case two factors in the denominator. We are going to break this up into sum a over x minus 3 plus b over x minus 2. So we write down one fraction for every single factor, but don't need to look at the x right here. Just ignore the x, and in this case just assign letters. Now, if we had, for example, two more factors, let's say I had even something like 3x plus 7 and x minus 5, well, we would have written something like this: c over 3x plus 7 and d over x minus 5. Well, it's not the case. We just have two factors, all right? Now, our job over here is to find the constants a and b that when combined back together would give us this x over x minus 3 times x minus 2. How do we do that? Well, so this is what we're going to do. I'm going to rewrite this equation. So notice in this case we're following a sequence of steps, but I'm going to create an equation with the last a couple of steps. I'm going to use a different color so you can see the difference. So x over x minus 3, x minus 2, a over x minus 3, b over x minus 2. Well, we need to simplify this equation. And well, by simplifying the equation, we mean to get rid of all the denominators. And we do that by multiplying both sides by the least common denominator. And in this case, the least common denominator, again, is that quantity that cancels out every single factor that you see in the denominator of every single fraction. Well, so in this case, the LCD would be the product of these two factors, that is x minus 3, x minus 2. So what happens when we distribute this? Well, so when we distribute this, notice how everything cancels here, leaving us with x equals to, well, when we distribute these two, x minus 3 times x minus 2. So check this out. We would be multiplying x minus 3 times x minus 2 times a, but notice how the x minus 3 cancel out, leaving us with a times x minus 2. When we do the same over here, distribute with the second term on the right hand side of the equation, well, notice how this time the x minus 2's cancel, leaving us with the product between b and b and x minus 3. Up to this point, are you guys following me here? Okay. This equation that we just found, it's even simpler than the one in the previous step. And this is the equation that we are going to use to figure out those constants a and b. So we will call this our basic equation. This basic equation, we're going to use it to find those constants a and b. Now, if you think about it, this is only one equation, but 1, 2, 3 unknowns. Well, two of the unknowns are a and b, the ones that we found, and well, x is technically not an unknown because that's the dummy variable for the expression that we're working on. Now, how are we going to solve a system of it? Well, actually, it's not even a system. It's just one equation that contains two unknowns. Well, so here we need to use our number sense. We need to think of clever values that will zero out one of the terms, and then we would be able to find on one step find A, and on another step find B. Can anyone think of a clever number to plug in that zeroes out one of the terms for x? 2. Okay, so for x equals to 2, so we're going to plug in the x equals to 2 everywhere we see the x. So that is 2 equals to A times 2 minus 2 plus B times 2 minus 3. Let me write down those 2's. And what's going to happen here? Well, 2 minus 2 is 0. 0 times A is, well, that's just 0. And 2 minus 3, isn't that a negative 1? That's a negative B. And that equals to 2. So B equals to negative 1. Alright? Wait, negative 2. Negative 2. So that's one of the unknowns. Let's find out the next number. Can you think of another clever value that could help us zero out one of the terms in the same way we did before? How about 3? Well, the number 3 sounds good. Sounds like a plan. Well, so for x equals to 3, let's see what's going to happen. So 3 equals to A times 3 minus 2 plus B times 3 minus 3. And that's going to cancel the B, and we will be able to find A in a similar way that we were able to cancel out the term containing the A to find B. So that's a 3 and a 3. This will be 0, and this is 3 equals to 3 minus 2 isn't just 1, that's just A. So we just found those constants A and B. And now we may go back to the original problem, the one that we decomposed the fractions together. So A, which is 3, and B, which is negative 2. And well, in this case, you might want to clear these signs right here. And that's final answer. And I did this on purpose to start with one example, doing in one direction, and then do the same exercises backwards so you can see that it's going to be the same result going back and forth. Now you can see the difference between combining the two fractions together versus decomposing this into partial fractions. Now, maybe when you cover these operations with rational expression, in some cases it were a nightmare to simplify. However, I mean, I don't want to scare you about this, but partial fraction decomposition can even be more stressful. It's going to be more involved than just combining. And I mean, this one is one of the simplest cases right here. It took a good minute to solve. But well, we're going to do a bunch of exercises of this. Okay? All right, let's see what's next. So how about we get started with the calculus? So now that we reviewed a little bit of the algebra related to this, let's integrate using partial fraction decomposition. For example, example number 2. Integrate x over x squared minus 5x plus 6. Well, so number 1, if we were to use the u substitution, for example, and I mean, that's something that you usually try first. U substitution, maybe you're lucky, it works, that's final answer, there's nothing else to do. However, So that's u equals x squared minus 5x plus 6. du would be 2x minus 5 with respect to x. Alright, well in this case we have this x right here, but we're missing that 5 minus 5 and that's 2, so we would need to do a bunch of adjustments in here, which is doable, but I think it's going to be too messy. So in this case, yes, even though partial fraction decompositions look like longer problems, I think it's a more efficient way, it's a better way to go about this kind of integration problem. So, well, let's erase this because it's not going to be relevant to this problem. Well, I'm not going to do the partial fraction decomposition again because, well, that's the same. Let's just use the result from the previous exercise. So we're going to write this integral, and that's going to be equal to the integral of what we obtain in this case is 3 over x minus 3 minus 2 over x minus 2. Well, let's split this into two separate integrals. That's going to be 3 times the integral of dx over x minus 3 minus 2 times the integral of dx over x minus 2. Well, now that we did this partial fraction on this big quotient that we had before, well, we may go ahead and integrate this to simpler integrals. And well, any ideas on what the results for this would be? Both are natural logs, right? Those are simple natural, and you don't even need to show the u du because, I mean, when the coefficient, the leading coefficient is 1, that's fine. Just go from here to 3 ln of absolute value x minus 3 and minus 2 natural log of x minus 2 plus c. That's all you need to do in this case. No need to show the u du substitution unless you have something more, more elaborate. For example, an integral that looks like this. The integral of, I don't know, 3x cubed plus 7x and 9x plus 7, 9x squared plus 7 dx. Well, in this case, yes, this one is the direct derivative of this expression. That's fine, but still, in a situation like this, it's better to show the u du just to make sure everything works. But something simple like this, no need. Okay. Well, so that's one example, one basic example on number 1. How do we combine fractions together? But most importantly, how do we do the problem backwards, which is the tool that we need for this topic, which is the partial fraction decomposition. Okay, so on the next page, we have like the steps to decomposing those fractions into partial fractions. Well, number 1. If you have an improper rational expression, do the polynomial long division. Well, what do we mean by improper? Well, this stems from the same definition actually of improper and proper fractions with numbers. Well, so let me write a couple of fractions and you guys will tell me which one is improper, which one is proper. Okay, 3/4. Proper or improper? Proper. 7/4. Proper or improper? Improper. And how do we know between proper and improper? So proper when the numerator is smaller than the denominator, and improper when the numerator is the same or larger than the denominator. So that's why this one is improper. And improper fractions are further described as mixed numbers. That's going to be 4 and 3/4. That is basically divided two numbers. That's the quotient plus the remainder over the divisor, and that's the idea that we're going to use when we divide these polynomial expressions. What about 5 over 5? Proper or improper? It's also improper, right? It's improper, and and in fact it's an integer. It's a whole number, but it's called, what we call it, an improper fraction. Well, what does that have to do with polynomials? Because, well, we're not going to integrate numerical fractions, of course. Well, in this case, improper, let me write this down. Improper when the degree of numerator is greater than or equal to the degree of the denominator. On the other hand, the rational expression is proper when the degree of the numerator is less than the degree of the denominator. So with numbers, we went with the value of the number. Smaller number than in the denominator, improper. And in this case, for polynomials, well, we don't go with the values. We go with the degrees of this polynomial. So smaller degree in the numerator than in the denominator, it's proper. Otherwise, greater than or equal, that's improper. And well, that's our first number one, our step number one. If improper, divide via polynomial long division. The second step is to factor the denominator, because from there we will split these fractions, these partial fractions, into, well, depending on what we have. So we need to write out our partial fraction decomposition, and well, whenever the factor in the denominator is linear, the numerator of the partial fraction is going to be a constant. Well, this is important. Let me highlight. If the factor is linear, the numerator is a constant. And whenever we have repeated linear factors need different partial fraction for each power. I will go over one example like this, and I will explain why do we have to write it down for each single fraction. And then whenever the factor is quadratic, and by the way, quadratic has to be a quadratic, irreducible, because in this case we are only working with polynomials that are factored over the rational numbers. Okay, if we get like anything like irrationals or polynomials that are, yes, quadratic polynomials that factor into complex numbers, no, we don't. We call it a quadratic irreducible. For complex numbers, well, you will deal with those when you get to complex analysis, when you take those higher levels of math. For now, we're going to limit ourselves to work only with rational numbers. All right, so let's go ahead and do another example here. Well, so number one, what do we have? The integral of 2x minus 1 divided by 4x squared minus 9. All right, so let's go and checklist the steps. Number one, do we have any proper fraction here? Why or why not? How do we know this one is not improper? Exactly, the degree in the numerator is smaller than that in the denominator. All right, sounds good. Okay, so let's see. So the next step is to factor out the denominator. So let's focus on the denominator, and hopefully you recognize the form in the denominator. We have quantity squared minus quantity squared. Isn't that a difference of squares? So let's factor the difference of squares, and that's a 2x minus 1, and that's a 2x plus 3, and 2x minus 3 with respect to x. Well, now that we factor the denominator, it's time to write down our partial fractions, and that's our next step. To write down our partial fractions, ignore the numerator. Even if it's the craziest expression in the numerator, just ignore it. Of course, we're going to use it when we set up our basic equation to find out the values of a and b or c, d, depending on how many factors we have. Well, so that's the integral of a over 2x minus 3 plus b over 2x plus 3. I'm going to change the order here. Alright. So our next task is to set these two quantities together without the integral symbols, without the differential operators, and treat it like an equation. That's what I'm going to do right on the side. Okay. So I'm going to go, I'm basically copying and pasting this. 2x over 2x minus 3, 2x plus 3 equals to a over 2x minus 3 plus b over 2x plus 3. Well, that's a very complicated equation. Let's simplify this equation. Yes. Minus 1. Yes, minus 1. Thank you. Minus 1. So let's simplify this equation by multiplying both sides by the least common denominator. And in this case, the least common denominator will be that quantity that will divide both the 2x plus 3 and the 2x minus 3. In this case, it would be the product of the two. 2x minus 3, 2x plus 3, 2x minus 3, 2x plus 3. And in the same way that we did in the previous example, multiply, distribute, but check how these two actually cancel, leaving us with 2x minus 1 equals to, let's do the same on the right hand side. So 2x minus 3 to x plus 3, multiply with the first fraction, see how the 2x minus 3's are going to get cancelled, leaving us with a times 2x plus 3. Plus, let's do the same, distribute on the second term, but this time see how the 2x plus 3's terms get cancelled, leaving us with b times 2x minus 3. Okay, up to this point, you guys following me here? So far so good? Yes. 2x plus 3, 2x minus 3. Oh yes, I had two of them. That's a plus, that should be a minus, right? Yes, thank you. Alright. So this will be our basic equation. And this equation, it's the one that we're going to use to find the constants a and b. So we use the simplest one, not the ugly one. Alright? And here is the part where we will need our number sense. Okay, can we think of a clever number to cancel out one term so we can find one of the constants? Negative 2 over 3, negative 2/3. So for x, negative 2/3, well, what are we going to get? 2 times, oh, 3/2, right? Negative 3/2. Yes, negative 3/2. That's fine. Yes, it's still morning, so, okay, so 2 times negative 3/2 minus 1 equals a times 2 times the negative 3/2 plus 3 plus b times 2 times the negative 3/2 minus 3. Let me plug in. Right, and let's simplify each term. Number 1. So 2 over 2 cancels to give us a negative 3. Negative 3 minus 1. Well, let me write down that negative 3 minus 1. And cancel the 2's, that's a negative 3. Plus 3, which will get zeroed out this time. Plus b times 2 over 2, that's a negative 3 minus 3. And well, let's do the arithmetics here. So that's going to be negative 4, and that gets zeroed out because negative 3 plus 3 equals to 0. And negative 3 minus 3, be careful with the addition. In this case, minus 3, still subtract 3. That's a negative 6b. Alright? Solving for b, that is by dividing both sides by negative 6, it will give us a b equal of 2/3. Okay, so we got one of the constants already. Let's find out the second constant. Okay, let me check my spacing here. Oh, that's fine. That's correct. Okay, can we think of another clever number that we can zero out the other term? So we already used x equals to negative 3/3 to zero out the first term on the right hand side so we can find the value of b. How can we find the value of a? What value of x can we use? The positive, its counterpart, right? So for x equals to 3 over 2. Okay, so what are we going to do? Substitute. 2 times 3 over 2 minus 1 equals a times 2 times 3 over 2 plus 3 plus b times 3 over 2 and minus 3. So 3 over 2, 3 over 2, 3 over 2. Okay, let's simplify this numerically well. The 2's here cancel. That's going to leave us with 3 minus 1. And then the 2's cancel. That's going to leave us with a equals 3 plus 3. Plus b times, cancel the 2's. That's going to leave us with 3 minus 3. And well, this is where the term cancels out. And now we will be able to find the value of a. So that's 3 minus 1, that's a 2, equals to a times 3 plus 3, which is 6a. And divide both sides by 6. That's a equals to 1/3. So we got the two constants that will split the fraction into two partial fractions. Well, let me zoom it out a little bit. And now that we've finished solving this part of the problem, we may go back to the integral and substitute where it corresponds. So in this case, well, let me just highlight a equals 1/3. That's going to go here. And b equals to 2/3, which is this constant right here. So let's go back to the integral. So that's going to be the integral of a, which is 1/3 over 2x minus 3 plus b, which is 2/3 over 2x plus 3 with respect to x. So let's focus on the integral. And in a very similar way, how about we take out the constants and we write as individual integrals. That's 1/3 integral of the x over 2x minus 3 plus 2/3 integral of the x over 2x plus 3. Right? So from here, We may integrate these two using the ln rule, and in this case you don't need to show the u du, because again this is one of those simpler cases that you don't need to. So that's a 1/3. I'm going to leave some space. Ln of 2x minus 3 plus 2/3. I'm going to leave a space. Ln of 2x plus 3. And those spaces I'm leaving are for those factors that come out of the integration of these linear functions, or using the ln rule rather. That's going to be 1/2 and 1/2. Well, in this case, divide out the 2's, plus c, and that's going to give us a 1/6 ln 2x minus 3 plus 1/3 ln 2x plus 3 plus c. And that's final answer for this exercise. Question?
Can you explain where those 1/2 come?
Yes, where did those 1/2 come from? So what if I did the u substitution for, I think this is something that I would like to, that's a good question, I should cover this. I mean, whenever we have something with integrals that are this simple, like the integral of 1/2x plus 3, well, you would set u equals to 2x plus 3, then du equals to dx. That means dx equals to 1/2 du. So when we do the u substitution, that's dx becomes 1/2 du and 1 over this quantity, which is u. And then this 1/2 would just be taken outside of the integral. That's where that factor is coming from. In a similar way, whenever we have the integral of, for example, cosine 3x dx, well, if we were to do the u substitution, u would be 3x du equals 3 dx. Then dx equals to 1/3 du. That's why when we integrate this, that's cosine of u, 1/3 du. That's why I usually skip this u du for integrals that contain very simple, angles or denominators or radicands or exponents. But whenever there's something more complex, like in this case, let me erase this. The integral of 6x to the 7, cosine, for example, x to the 8th, or 4x to the 8th. Well, in this case, it may not be that easy to just do this in our heads. In this case, it would be a good idea to show the u du part. U, in this case, 4x to the 8th, du equals 32, x to the 7. Well, we have the x to the 7. That means x to the 7, dx. dx equals 1/32 du. So when we do the substitution, let me continue here. I'm going to take this 6 outside of the integral, cosine of u, and x to the 7 dx becomes 1/32 du. So as you can tell, for a problem like this, it's not that easy to do it in our head like in a single step, in the same way that we did it for more simpler integrals. In this case, it's better to do and show the u substitution. So 6/32, that's going to be 3/16, I guess. And cosine u du, and well, whatever that integral is, right? So again, in cases more elaborate, that's the u sub. In cases more simpler like this, just divide. Another way to see this, for example, okay, another point of view, for example, when we have the integral of e to the 5x dx versus differentiate e to the 5x. So let's find the derivative of e to the x. What's the of e to the 5x? What's the derivative? Isn't it itself, first of all? 5x, e to the 5x times by mini chain rule times 5. So essentially, what did we do? Get the exponential and multiply by the derivative. However, in the integral, for example, we need to do which is the reverse of the differentiation. That's going to be the integral of the exponential, which is itself, e to the 5x, plus c, but in this case, because for the derivative, we multiply by that constant multiple. What do we do for the integral, which is the reverse? Divide, right? And in this case, again, you don't have to show me the u du for something this simpler. Just go, oh, the reverse process of the integral, we do the reverse process of multiplying those coefficients. That's valid on the test. So unless, again, you get something more elaborate, all right? Okay, guys, so for the next example, I don't think I'm gonna have enough time in 6 minutes because there's a number of aspects that I really need to go over in detail so we can get through this example. But we're gonna have the entire week to cover this, so don't worry.